Our next speaker is Yang Yang. Yang Yang is an assistant professor of civil engineering at the University of Hartford in Connecticut. He received his PhD from Missouri University of Science and Technology in Rolla, Missouri. That's also my alma mater. And his MS and BS from Tongji University in Shanghai, China. Before joining the University of Hartford, he worked as a structural engineer for a design firm in Overland Park, Kansas. And he is an active ACI and ASCE member and conducts research and development of finite element models for concrete structures and applications of FRP and FRCM and repair and retrofit of concrete members. And with that, I would like to hand it over to Yang Yang.
Thank you, everyone, for being here. And thank you, Gary and Eva, for your organization of this session and your coordinates in the publication of the AASHTO. Here, I would like to talk about our paper about the design example of a bridge pier cap beam considering torsional effect and per AASHTO design specifications and ACI 31819. And this work is done with the collaboration by Dr. Rainey Her. She's a project manager from Gaver, and with also by Dr. Nestle Sneed. She is a professor from Missouri University of Science and Technology. So here is the problem statement. As you can see on the top of the slide, so we worked on a three-span bridge, and all the three spans are simply supported by the middle two piers and the apartments on the two sides. As you can see here, the middle span of the bridge is much longer than the side spans. So when you apply the live load and the dead load, the reaction forces from the longer span will be much larger than the reaction forces from the shorter span. So if you look at the cross-section view of the cap beam over there, as you can see there, the red denotes the node from a longer span. So that is bigger than the node from the shorter span. So there is a torsion, and the torsional moment is very significant for this type of construction. So when you do design, especially when you design the reinforcement there, you do need to consider the torsion induced by the difference in the load from the longer span and the shorter span there. So here we did a very structural analysis using a 3D model of the bridge so that we can get the envelopes for the shear force, bending moment, and the torsional moment. As you can see here, for the shear and the torsion moment, we just convert all the shear and bending moment to absolute values, so because the negative and positive shear and torsion does not make much difference there. But for the bending moment, we do consider the signs, because if you have positive and the negative moment, the location where you have the longitudinal reinforcement is different in the two cases. So to simplify the example in our paper, we just use the maximum values on the three envelopes so that we can have a very conservative design over there. Firstly, we did a design per the AASHTO LRFD bridge design specifications. So that's the latest version we used. And for the flexural design, the flexural design is pretty much typical. For most of the engineers, we can determine the area required for the flexural moment. And we also did the shear and torsion design separately there, so that if we add the required areas for shear and torsion, we can have the required total transverse reinforcement. So one thing for the AASHTO LRFD is when we use AASHTO LRFD, we do need to consider the flexural torsional moment as well as the shear to determine what's the additional longitudinal reinforcement required there. So there is an equation provided by ACI, provided by AASHTO LRFD, so that we can determine the total longitudinal reinforcement required there. So this is a typical procedure that you can use for cap beam design and per AASHTO. And we also listed the procedure for ACI 318 design method over here. So very similar to the AASHTO design procedure, and we did the flexural torsion design and the shear design separately. And one thing is for torsion, ACI 318 requires some additional reinforcement there. So if you add the additional reinforcement to the longitudinal reinforcement there, so that you can come up with the required total longitudinal reinforcement there for the section. So in order to compare the two approaches, we summarized all the design equations from the two design codes there. So as you can see here, when you look at this table, you want to be aware of that in ACI, all the units for the F'(C) and Fy or Fyt, they are in PSI, while in AASHTO, the F'(C), Fy, and Fyt, they are in KSI. So we converted all the units to KSI. So all the numbers shown on this table is in KSI. So if we did that conversion, we can clearly see the difference of these two approaches. As you can see here, most of the equations used the two codes are very similar to each other, but there are some difference there. The major difference is the strength reduction factors for shear and torsion design. As you can see here, the AASHTO uses 0.9, while the ACI 318 uses 0.75. And another difference is how the AASHTO and the ACI 318 considers the additional longitudinal reinforcement there. So as you can see here, in the AASHTO design code, the additional reinforcement is calculated based on the consideration of the interaction between bending, shear, and torsion, while in the ACI 318, the additional reinforcement is only a function of the required torsional moment there. So that's the major difference there. And based on the design equations, we come up with the design on the quantities of the shear and torsional reinforcement that is required. So as you can see here, most of the numbers for the two methods are very close to each other, but there are some difference here. So one major difference is for the shear design. As you can see here, if you use ACI, the resulted shear reinforcement, the quantity of the shear reinforcement is almost double the quantity of the shear reinforcement if you use AASHTO. But for torsion reinforcement, the quantity per these two different methods are pretty close to each other. Even the AASHTO use 0.9 for the strength reduction factor, and the ACI use 0.75 for the strength reduction factor. The resulted quantity for the shear reinforcement, for the torsional reinforcement, would be very close to each other. And another comparison is made between the additional reinforcement in the longitudinal direction, and we found that even the two approaches use different equations, and one considers the combination and the interaction between shear, bending, and torsion, and the other one is only a function of the torsion, but the resulted additional longitudinal reinforcement is pretty close by these two methods over there, as you can see. And after we finish the determination of the required quantity for the shear, torsion, and the flexural reinforcement, we did some detailing work. So when we started doing that detailing work, we, besides the consideration of the maximum spacing of the transverse reinforcement in the longitudinal direction, there are some specifications by ACI 318 on the transverse spacing of transverse reinforcement. That means there is a limit on the maximum spacing that you can use between two adjacent legs of the transverse reinforcement. So in ACI, so there is some specifications there for you to determine what's the maximum spacing you can use. But AASHTO does not provide a similar equation. So we did some literature review, and we found that the Florida DOT, they did provide some limit on the maximum transverse reinforcement that can be used in a section. So we compared these two methods, and we found that looks like the ACI is a little bit stricter on the maximum and transverse spacing that you can use for section. And we thought probably the main reason was the ACI is mainly for building beams. So the building beams is typically is a little bit smaller than the bridge beams there. So that's why ACI is a little bit stricter over here. And after we determine the maximum transverse spacing over there, so we can tell how many loops that we need for one section. Because for our case, the width of the beam is about 6 feet. So looks like we do need 2 loops over there. So when we determine the size and the spacing for the transverse reinforcement, we need to consider the load path for shear and for torsion. As you can see here, if you consider the node resistant mechanism for shear, looks like there will be 4 legs that are effective to take the shear. But if you consider the load path for torsion, there are only one loop that is adequate, that is effective to take the torsion over there. So look, as you can see here, the outer legs will be subject to the combination of the shear and torsion. So the size of and the spacing of the outer legs will control the design. So we did use an equation, and you see it here, to determine the required quantity for the outer legs. So based on the quantity of the outer legs, we can have a determination on the size and the spacing for the transverse reinforcement here. So this is finalized the design sketch of the section view. So we showed all the information of the longitudinal reinforcement as well as the transverse reinforcement. And we compared the 2 joints here, and we found that the only difference is if we use the same size for the transverse reinforcement. So basically ACI is a little bit more conservative there, because ACI requires a 9-inch spacing, while the AASHTO requires only a 10-inch spacing. So I think the main reason is because the ACI 318 requires almost double the quantity for the shear reinforcement compared to the AASHTO's design methods. And we also found that AASHTO used a different equation to calculate the area enclosed by the shear flow for the section. So that even the AASHTO LRFD used a larger strength reduction factor, that resulted transverse reinforcement required for torsion is pretty much the same as the ACI 318. And we also found that even different equations are used to determine the additional longitudinal reinforcement for torsion. And the 2 approaches will give you a very close design, at least in our example over here. So I think that's all for my presentation. Any questions and comments here? Thank you for your time.
Thank you, Yang. That was great.
Thank you, Gary.
Are there any questions from the audience? So when you were considering the difference in the phi factors, I mean, there's also differences in the load factors as well for both methods, right?
Yes, the load factors is a little bit different, but yes, correct. but when we do the structural analysis, we did consider the difference between the node factors there. So the envelopes for the two different methods, they have different values there. Right.
And then did you try to maybe play with the theta, the factor of theta, to maybe adjust the demand for torsion between, you kind of shift that between the transverse to the longitudinal to see if you could, balance that out a little bit differently?
No, we haven't yet adjusted the beta number. We just use the recommended beta value for both cases.
Yeah, that makes sense. I just didn't know if you looked at that at all.
I have a question as well. While we wait, if something comes in through the Q&A. I'm going to ask you the same question as I asked Giorgio. What would be your main takeaway that you would give a designer who may be attending this session? What struggles did you find along the way, and what piece of wisdom can you give somebody who may be faced with a similar case in practice?
I would say that the major challenge in this type of design is the load pass. So especially when you consider the reinforcement for shear and torsion, when you do design, you need a clear understanding how the shear and torsion are resisted by the reinforcement, and which part of the reinforcement is effective to take shear and which part of the reinforcement is effective to take the torsion. So that's one major challenge is that when you have this type of design. And another thing is when you do this similar design, I would say you want to have a clear understanding on why there will be a torsion on your member. So for example, if you have a determinate structure, typically the torsion can be calculated very straightforwardly. But if you have an indeterminate structure, and there are a lot of other considerations, for example, the stiffness of the beam, the stiffness of the columns will influence your T sub U and M sub U there. So For bridge design, I would say, and typically engineers, when we practice the design for bridges, they usually simplify the load transfer between beams and piers so that they have a clear understanding how the load is transferred from the superstructure to the substructure. But in some cases, if you do have to have an indeterminate structure, you may have to work closely with some engineers with more experience in determining the torsion in the members. I think that's two major points that I have already observed from our work. Thank you.
All right, Young. So a question has come in from the audience. I'll read it to you. Hi, Dr. Young. Thank you for the talk. Could you give us more details about why the AT over S was similar, but AV over S was so different? The second part was it due to the values of theta being used in the AASHTO calculation, or A naught? Third part was, or was it because VS required was different between the codes?
Yes.
Okay,
yes, pretty much similar to Gary's question. And the reason why the AV over S is so much different over here is because, firstly, as you can see there, for the strength reduction factors, AASHTO use 0.75 while using 0.9, while ACI use 0.75. And another thing, the reason is we haven't considered with the adjustment of the beta values there, we just use the default value. So that I think that explains why their numbers are so different here. But for torsion, we use the recommended value by the two codes, and so that their values are pretty close. And even, and the torsion we use 0.9 and for AASHTO and 0.75 for ACI. But for torsion design, AASHTO use a smaller A0 number, and the ACI use a bigger A0 number, so that the two methods will result very close. Even the two approaches use some a little bit different parameters there, and they will result the same quantity for the reinforcement here.
All right, that's great. All right, I think we need to move on. Thank you so much, Yang, for that. It was a great presentation. I think it was great to see that comparison between the two methods.
Thank you, Gary.